Hi, welcome to the Calculus 3 lecture series. And we are in this unit, Vector Calculus. And this video we're going to talk about is our lecture number 3, Vector Field. In the previous two videos, we started, the first video is to define the vector functions and the domain, range, limits, those things regarding to the vector function. Then the second video, we talk about for the vector functions, how do you take the derivative integration? And now the third topic, we're going to introduce a new things. We call it is the vector fields here. Okay, so let's go ahead and go to our lecture notes here. Okay, so the first things here. Okay, so a vector field. Okay, so that means the key things, let's say here. Okay, so the key things here, what is the domain of the vector field, right? So the domain is a set D. Okay, so that means each point, so it's a point, right? So for a set in the R2, you have so many different points, right? So in the set D in R2, as the functions, okay, the f's here assigned to each one. So for this function f here, right? So for this function f here, then for each point, you give this point a vector, okay? Okay, so you give this pointer a vector. And that's why we call this is the, this is, we call this the vector field. So that's why we say the domains are point and the range, the elements are vectors here, all right? So the domains here, they are just the points in a given area, these here. And so like for the vector fields here, we can write that f of x, y, px, yi, because for every given point, x, y's, right, you have a function, you give it to a vector. So this is I and j's here. And then we have a special name for this. We call this a scalar field components functions here. So those are my component functions here. So this is how do you define the vector field in R2, right? So we know is in R3, we can do the similar way. So that means for every point in the R3, right? F of x, y, right? So then you can define the vector. And the vector, you have those functions, right? So for the I components, you have a px, yz is a function of x, y, z. Then for the j, you have a components. So this is a components j's, right? So you have a function qx, yz. And then for the case here, you have a function rx, yz. So this is a case here, okay? So let's take a look exactly what is in the real life, what type of the things we are thinking about the vector fields here. Okay, so the first things here, let's just get familiar with the terminology. I know this topic probably is very, very new to many people. When you calculus 1, calculus 2, probably you never talk about this. Okay, so now for a given vector field. So first here, so the first problem is we just want to get familiar with what is a scalar field components. So that means what is this ones here? So I know, so for this ones here, that means my scalar field for the I components will be what is a cosine axis, right? Then for the Q, XY will be what is a sine XY. That means if you give me any point XY, so I change it to a vector. So the vector's I components is a change to XY based on this function. And then to change it to the J is based on the function sine XY. That's what we call these two. We call it a scalar field components, right? So let's make sure we understand those terminology. It's a pretty new terminologies here. Okay, so now for the Second one's here. So this is R3, right? So we should have 3 scalar field component. So the first one is PXYZ. So what is the first one? Is x squared plus y, right? Then the QXYZ. What is this one? Will be 0, correct? Then the RXYZ. What is this one's here? It will be y squared plus z. Okay, so this example is pretty easy. We'll just basically is just to show you, how to find what is the terminology for the scalar field. Okay, so now let's take a look at what is the vector fields here. So like in here, so let's take a look at the example for the f of x, y. So this is how do I define the function, right? So this is my scalar field function, absolute value and absolute value of y here. Okay, so let's take a look. They said let's sketch the point 0, 0, -2, -3, 1, 2, and 2, 2. Okay, then here I'm going to show you how to use the calcplot 3D to verify it. Okay, so let's take a look here first. Okay, so F, right? So we have a first point is F0, 0. Okay, so the F0, 0, you put the zeros here. So what do you have? You have 0i plus what? 0j's here. So what is here? So this is zeros, right? So this is a component. So this is a vector at 0. So let's see here, because it's here at 0, 0, but it doesn't have any magnitude. So it's just the point. All right. Okay, so now the next point here, this is the F, -2, 0. Okay, so you put it over here, right? So the -2 zeros here, what is that? So this is the -2, the I plus 0j's, right? So what is here is a 2i, and the 2i, so I know because 2i, and then the magnitude of the 2i is just what? It's just 3, right? So that means -2, 0 at here, this one is a starting point, right? Then my vector will going to go, maybe I use a different color so that it's good. So it's not going to mix up with my other color here. Okay, so let's see here's 2 zeros, right? So I start -2, 0. Then the length is 2. So this is my vectors here, right? So this is my vector. So this is my vector at -2, 0. Okay, now let's take a look at the next ones here. F of -3, 1 here. -3, 1. So this will just be 3i plus j, correct? Okay, so this will be the 3 y plus j's, right? So, okay, so now let's take a look at what is the magnitude of the 3i plus j. What is length? Because we know the vector, you have to have a point, and also, you need to have a length, right? Okay, so now let's take a look here. So the length here is what? The length here is 9 plus 1, so it's equal to the square roots of 10 here. Okay, so now let's take a look at how do I graph this vector. I'm going to use the different colors here. Okay, so this one's here at the point -3, 1. So I'm starting at here, right? And I'm creating this vector is 3i plus j. That means the 3 to the I is 1 to the j. So this is 1, 2, 3, right? Then 1 here, right? Okay, so this will be my vectors here. So if you take a look at the length of here is the square root of the 10th here, right? Because it's here, right? So it's square root of 10. So You can use that to verify, so you don't have to always calculate that. Okay, so now let's take a look. The next ones here is 1, 2 here, right? So the 1, 2 will just be I plus how many? I plus 2j's here, all right? So let's take a look. Let me see, I can have, let's use the red again. So because they are far away. So 1, 2, that means I'm starting where? I'm starting here, right? I'm starting here. So now is I is 1, J is 2, right? So that means I go right 1, so 1, 2. So here will be, so this will be my, so this was the vector. So if you take a look, the length of this one will be what is 1 square plus 2 square will be equal to the square roots of the 5, right? So that's why we know the length of the I plus 2j is equal to the square roots of the 5. You cannot verify here. Okay, so now we have another point here. This is 2, negative 2. So now the 2, negative 2, you will get what? You will get 2i plus 2j's, right? Because the absolute value of the y is 2. Okay, so now let's take a look at these ones here. I'm using different color. Okay, so it's 2, negative 2. So I'm starting here. All right, so now I'm going to be a 2. So I move up to 2 and 2. So we'll be here, right? Okay, so this will be the vector associated with, the associated with the point 2 and the negative 2 here. So if you calculate the length of this vector, so this one's here is 2i. Okay, so 2i plus 2j. Right, so it will be the square root of the 8 here. So that's what we call this the vector field. So of course you have infinity numbers of the vectors here because every point you can generate a vector, right? Based on these functions here. So that's why we have a software can help us to do, to do the plotting here. So let me show you how to use the softwares here. Okay, I'm going to leave the lecture notes here and go to the website for the softwares here. So let's go and over here. Okay, so when you call on the Calc Plus 3D, so this is default, you can uncheck this. Okay, so you can uncheck this and now see here, this software, that's why I say it's pretty useful for Calculus 3. So you can select the graph. What you want to do here? You want to do vector fields, right? So you want to do vector fields. So the first one, the first scalar field is the absolute value of x. And then here, this is the absolute value of y here. And the p, that is for the z, because this is R2, so I set p equal to 0. And then I plot it. See, that's what is the, that's what is the vector field. So if you take a look to the, to the xy, right? So if you take a look for the xy directions here, you see that, all right? So it's kind of, you can play with it, right? So you see what is the xy direction, the vector fields looks like. So it's pretty useful software and you can help you and try to take a look here. Of course, here you can choose how many vectors you want to plot and so how dense is the vector you want to see here, all right? Okay, so I hope that you will have a chance, to try it. So here, this is the output for the, the vector field from the from the software, so it can help you to create the vector field and give you a vision what it looks like. Okay, the next one is here. We're going to talk about is one thing is very important. Okay, so we said the scalar function. So if you give me a function, z equal to the f of y, we know the gradient del is a vector field, right? Because we know the gradient del, but that's how do we define the gradient vectors, right? So we say it's partial x, partial y here, okay? So the gradient vector, in fact, is a vector field, so, right? Because for every x, y, you know, you can use this function to create the scalar field components for the I. For this one, you can create the scalar field components of J's here. Now in here, we are introducing one very important, you know, the concept. So we say if a vector field is a conservative, okay, that means f is the gradient vector for some functions. That means f is the gradient vector for some scalar functions here. So this is very, very important definitions, right? So we said if this vector field is a conservative, then later we're going to talk about why the conservative is so important, right? Why it is good, all right? So that means f, there is some scalar function, f of xy, then f is the gradient, you know, the gradient vectors for these functions here. And then this f functions here, the lower f, we call this the potential function for the f's here. Okay, so let's kind of practice this concept and then try to gradually, you know, get into the more deeply there. So first, let's take a look at what is a gradient vector field. All right, so we know the gradient vector is just the partial for x. So what is here? 2x plus what? 3y. And what is the partial here? This is 3x, right? So what is my gradient vector field? The gradient vector field xy will just be these two, right? So will be the 2x plus 3y I plus 3xj here. Okay, so now the same ways here. So this is what? This is my pxy's, right? That's scalar components. This is what? qxy's here, right? Okay, so let's take a look in R3. So R3 is the same here, right? So that means the partial x. So what is here? So 2xy plus z squared. Partial y, what is here is x squared plus 2z. And the partial what? The partial z is what? 2xz plus 2y here, right? Okay, so now I can write the gradient fields here. X, y, z will just be what? It's 2xy plus z squared, right? So this is what? This is the I. Then this is x squared plus 2z. What is here? This is the j. And then the last one is 2xz plus 2y. What is here? This is the case, right? So just like we say, you can say this one is my scalar components function. You can say this is x, y, z. What is here? You can say q, x, y, z. And what is here? You can say r, x, y, z here. Okay. Okay. So now the next thing here is if f is a conservative field. So this is just try to emphasize the definition. So if f is the vector field, then what's that mean? So that means f is going to be equal to the del f for some scalar functions, right? So if f is a conservative field, then the f has to be some type of the gradient, the gradient functions for the for the scalar function f's here. So in the next section, we're going to say, how do I find these scalar functions here? Let's take a look at one simple example before we go any further, right? So the next section, we're going to dive deep here. Okay, so the first one, this one is, they said, yes, this one is a conservative. Okay, so we say, if this is a conservatives, right? That means there exist f functions. And then we know this f here will be equal to what? Will be equal to the del f of xy here, right? Okay, let's take a look here. So this is f of x. So if this is conservative, so let's say here, let's assume this is conservative. So let's see, I can find this f of x, y. So I know if the first one is a what? This is 2x, right? And what is the second one is here? This one is 2y's, right? Okay, so now if I integrate up, so I can find, so here I can get like f of xy is equal to kind of x squared plus y squares, right? So see here, if you do the partial for x is 2x, you do partial for y is 2y's, right? So we say, yes, right? So we say, yes, f is conservative. Okay, so f is conservative because what? Because we can find the scalar functions f of xy equal to the x squared plus y squared, right? Is one of such function. You might have like you can find many of them. It's possible, right? So because I can find one scalar functions and the gradient vector functions for this one is equal to the capital F of x, then we say capital F of xy is a conservative. Okay, so that is for this section. It's a pretty easy section. So the key things to remember is how do you graph the vector field? Okay, how do you graph and what's that mean? And then the next things here you need to know is what is the definition of the conservative. We're going to use this definition a lot. All right. Okay, that's it. It's easy sections here. All right. So let's stop here and I will talk to you in the next sections here. Okay, bye-bye.